planes of oxygen atoms with silicon and aluminum ions. So in the last class, I told you that it is made up of a tetrahedral structure and an octahedral structure. So it will have one silicon atom or one aluminum atom surrounded by oxygen atoms bonded by hydrogen ions or hydroxyl. So most of the silicate clays are made up of planes of oxygen atoms with silicon and aluminum atoms holding the oxygen together by ionic bonding. Therein, it attracts the positive and negative charged atoms. Like this, 3-4 planes of oxygen atoms with intervening silicon and aluminum ions make up one layer. So one layer means one silicon layer, one aluminum layer. See, the diagram also have drawn. So one clay particle is composed of many layers placed one above the other, like deck of cards. You have seen pack of cards. So one card is placed over the other means, so clay is also made up of one layer placed over the other layer. One layer is silicon layer, one layer is aluminum layer, silicon layer, aluminum layer. So like this, it is placed one above the other. So most silicate clays are called as aluminosilicates because they are made up of aluminum and silicon atoms. See the diagram, you can see a triangle diagram I have shown you, wherein it has 4 oxygen atoms, 1 silicon in the center. Because it is made up of 4 tetra, it is referred 4 oxygen atoms, it is referred to as tetrahedron. So the basic building block for the silica dominated sheet is a unit composed of 1 silicon atom surrounded by 4 oxygen atoms forming a silica tetrahedron. So you should know what is a silica tetrahedron. You will be asked, silica tetrahedron refers to 1 silicon atom surrounded by 4 oxygen atoms. That constitutes the silica tetrahedron. Because of its 4-sided configuration, the unit is referred to as a tetrahedron, and it is supposed to have the 4-sided configuration. Therefore, it is referred to as it is having tetrahedral coordination. Here, the planes of oxygen are held together by silicon, are tetrahedral oriented and referred to as silica tetrahedral sheet. So that is clear now. So clay is made up of 1 silica tetrahedral. Next, I will share the oxygen tetrahedral sheet. 1 minute. The tetrahedral. So see the tetrahedral, next is the octahedral sheet, the aluminum octahedra. Octa means 8, it is a 8-sided crystal lattice wherein aluminum is surrounded by 6 oxygen atoms. So here the aluminum octahedra is an 8-sided building block consisting of a central aluminum. You can see too, I have written aluminum in the center, aluminum ions or atoms surrounded by 6 hydroxyl or oxygen atoms. The large number of aluminum octahedra are bound to each other by sharing the oxygen atoms in an octahedral layer. They are arranged in a plane of forming aluminum octahedral sheet. So you can see in the picture, as well as already I have sent you the notes, wherein you can see 2 aluminum ions are connected to 6 oxygen atoms or 6 hydroxyl groups. So the normal oxygen to oxygen distance is about 2.60 angstrom unit, and the common hydroxyl to hydroxyl distance is about 3 angstrom unit, like this. So the thickness of the unit from this is about 5.05 angstrom unit in the clay mineral structure. So aluminum is Al3 plus, magnesium 2 plus. So sometimes instead of aluminum, it may be occupied by Mg2 plus. See, Al3 plus and Mg2 plus are said to have similar ionic radii. Si4, Al3, Mg2 plus. Only one valence difference, no. So those three can occupy each other's place. So when they occupy each other's place, only that is referred to as isomorphous substitution. Similar ionic radii they are said to have. So aluminum and or magnesium are the key cations in the second type of sheet. So an aluminum or a magnesium ion surrounded by 6 oxygen atoms or hydroxyl group gives an 8-sided building block. 8 means octa, 8-sided building block. Therefore, it is termed as octahedron. And the sheet formed due to aluminum is called as octahedral sheet. And suppose say this octahedral, because it is occupied by two aluminum atoms, is referred to as dioctahedral sheet. If the same sheet is occupied by magnesium atom, then it is called as trioctahedral sheet. So you should know the difference between octahedral sheet, dioctahedral sheet, trioctahedral sheet. So trioctahedral sheet means magnesium atom will be present in place of aluminum ion, and dioctahedral sheet means 2 aluminum ion linked with 1 silver tetrahedral sheet. So the difference or the distinction between this dioctahedral sheet and trioctahedral sheet is that 2 aluminum ions in a dioctahedral sheet satisfy the same negative charge from the surrounding oxygen and OH minus ions as the 3 Mg2 plus ions in a trioctahedral sheet. So for any substance to form, that is octet rule is there. Any substance to be stable, that octet rule has to be satisfied. Like that, similarly, here also, see, we know that oxygen valency is 6. It requires 2 more ions to be stable. So it gets that either from silicon or aluminum or magnesium. So it forms a diocta and trioctahedral sheet. So the next diagram is see the structure. You should know all these diagrams. It's visible, right? So you know what is a tetrahedral sheet? You know what is an octahedral sheet. So these two sheets only make up your clay structure. So clay means it has silica and aluminum along with hydrogen and hydroxyl. So like that, one tetrahedral sheet, one silica sheet per one aluminum sheet is referred to as 1:1 type of lattice. So the clay is said to have one layer of silica, one layer of aluminum. So then it is referred to as 1:1 type of clay. Example, kyanite clay. See, I've shown the diagram there. 1:1, one silica layer with one aluminum layer. Then 2:1 type of lattice means two silica sheets. Two silica sheets, and in the center is the aluminum sheet. So two tetrahedral, and in the middle is the octahedral sheet. That is referred to as 2:1 type of clay. Example, Mont Morillonite. So, now if you are supposed to ask to draw 1:1 lattice means you have to draw like this. One silica sheet attached to one aluminum sheet. 2:1 means two silicon sheets on either side. In the center, one aluminum sheet. That is 2:1 type of clay mineral. Example is Mont Morillonite. So like this, different combinations of these two general structural units. The structural units means you should remember it is the tetrahedral sheet and the octahedral sheet. These two sheets forms the structures of various layer silicates. Example like mica, vermiculite, montmorillonite, chlorite, kyanite, and other interstratified and intergradient layer silicates like chlorite, etc. So you should know the examples of this 1:1 type of clay and 2:1 type of clay. So clay is made up of tetrahedron and octahedron. Now, on the basis of number and arrangement of the silica and alumina sheets, silicate clays are classified into different groups. So based on that, it is classified into 1:1 type of clay minerals, 2:1 type of clay minerals, and 2:2 type of clay minerals. So 1:1 type of clay minerals, already it shows one sheet of silica layer, one sheet of aluminum layer. See the diagram I have shown you there. You can see the diagram. There are 6. I've shown you circles, 3, 6 oxygens, 1, 2, 3, 4, 5, 6, with 4 silicon, 1, 2, 3, 4 silicon. So in this 1:1 type of minerals, the layers of the minerals are made up of one tetrahedral sheet, that is silica sheet, combined with one octahedral aluminum sheet. Here the examples are kyanite, halloysite, nacrite, dikite. You should remember these examples. The tetrahedral and octahedral sheets in a layer of this kyanite crystal are held together by oxygen atoms tightly, which are mutually shared by the silicon and the aluminum cations in their respective sheets. So these layers are held together strongly by hydrogen bonding. Therefore, the structure is fixed, and there is no expansion between the layer when clay is wetted. That is why we say non-expanding. So these type of clays do not expand because the two layers are strongly fixed with each other by hydrogen bonding. You may be asked to write short notes on kyanite minerals, means you have to draw this and explain about the kyanite mineral. Here, in this mineral, cations and water do not enter between the structural layers of 1:1 type of mineral particle because they are so strongly bonded with each other. The surface of the kyanite mineral is restricted to the outer forces or to the external surface area. And there is little or no isomorphous substitution in this 1:1 type of mineral. Because of this less surface area, it accounts to low capacity to absorb cations because the surface area is very small compared to montmorillite or 2:1 type of clay minerals. So what is the shape of these kyanite minerals? You should practice drawing this. It's visible, no, that structures. So these kyanite crystals are usually hexagonal in shape. So when viewed under an electron microscope, the kyanite crystals are found to have hexagonal in structure, in shape, and in comparison with other clay particles, they are large in size, and the size ranges from 0.10 to 5 nanometers. And majority of these kyanite minerals, the range falls between 0.2 to 2 mm range. Because of the strong binding forces between the structural layers, kyanite particles are not readily broken down into further thin plates. Because they are strongly bonded, they cannot be broken easily. Then kyanite exhibits very little plasticity. Means that kyanite minerals cannot be molded into any shape easily because it has less plasticity property, less cohesive, and less shrinkage and swelling property. So these are 1:1 type of clay minerals. So far it is clear? Yes or no?
Yes, ma'am.
Huh? So you should know what are layer silicate minerals. Phyllosilicates means made up of horizontal layers which look leaf-like. Therefore, it is called as phyllosilicates. They are made up of tetrahedral, octahedral sheets. And if the sheets are joined together by hydrogen bonding, wherein one silica layer with one aluminum layer, it is called as 1:1 type of mineral. If aluminum is present between two silicon sheets, it is called 2:1 type of clay mineral. And sometimes there are clay minerals wherein two silica and two aluminum layers are joined to each other. They are called as 2:2 type of clay minerals. Among that, you should know the bonding, the distance between the oxygen atoms between one layer and the other layer, and the force with which is held. And this is non-expanding because they are so tightly held together that they do not allow cations or water to enter them. Therefore, they do not swell or they do not shrink because they have very less plasticity, cohesive, and swelling property. So that much is clear with respect to kyanite minerals. Next, coming to the 2:1 type of clay minerals. 2:1 type of clay minerals means the crystal unit layers will have one octahedral sheet, that is aluminum sheet, sandwiched between two tetrahedral sheets. So I will send that picture also. There is some power problem here in the department. Please wait. Switch current is going, current is coming. Okay. So 2:1 type of minerals. Here it has one octahedral sheet between two tetrahedral sheets. And among these 2:1 type of minerals, we find further classification as expanding type of 2:1 type of mineral and non-expanding type of minerals, 2:1 type of minerals. Example, expanding type is smectite, vermiculite. Non-expanding is muscovite mica, biotite mica. So coming to the first one, that is the expanding type of minerals, the smectite group has interlayer expansion. First point, it has interlayer expansion. First point, therefore, because of this expansion, it absorbs more water, it absorbs more cations. Therefore, it has the swelling property when it is wet, and when the water enters the interlayer space, the forces will move apart and the clay will swell. And when water is removed, again it shrinks. And because of high plasticity, it can be molded into any shape. So the crystals present in this type of clay are like flakes. Mica, you have seen mica sheets like flakes. They are composed of expanding lattice, and each layer is made up of, as already I told you, octahedral sheet sandwiched between two tetrahedral silica sheets. Here, there is little attraction between oxygen atoms in the bottom tetrahedral sheet of one unit and those in the top tetrahedral sheet of another. So this permits a ready entry of any exchangeable cations or water into the internal surface. Here, therefore, the internal surface is more compared to the external surface of the crystal, which is opposite of kaolinite. So in Montmorillonite, when in Montmorillonite, see this, when magnesium, suppose say you add magnesium fertilizers or any magnesium salts, it can replace aluminium in some sides of the octahedral sheet, and some silicon atoms in the tetrahedral sheet may be replaced by aluminium. I told you those three: aluminium, silicon, magnesium, having similar, not same. I'm not saying it is having same ionic radii. It has similar ionic radii, means equivalent ionic radii. So it can replace each other in the crystal lattice. Silicon can be replaced by aluminium. Aluminium can be replaced by magnesium. So this, like this, they substitute each other. That is called as isomorphism. Isomorphic substitution means substituting of ions of similar ionic radii. These substitutions give rise to negative charges. These minerals show high cation exchange capacity. They have wide cracks in the soils. You would have seen black soils, they have wide cracks. That is because of swelling and shrinkage properties, and because of presence of smectite dominated soils. So vertisols, black soils are called as vertisols, vertisols, vertisols. And you would have seen those black soils. They become very slushy if wet, and they become dry and form cracks when it is dry, black cotton soil. So these dry aggregates are very hard and difficult for plowing or for tilling. So another example of this 2:1 type clay is vermiculite mica, that is 2:1 type of minerals. So in this mineral, it will have octahedral sheet between two tetrahedral sheets, and here it has a dioctahedral sheet with one trioctahedral sheet. So here vermiculites are examples, and in this tetrahedral sheet, most vermiculite considers substitution of aluminum for silicon to take place, and this accounts for most of the creation of high negative charge associated with these minerals. So vermiculite, there will be more negative charge. Therefore, water molecules along with magnesium and other ions get strongly absorbed in the interlayer spaces of vermiculites. These act as primarily as bridges holding the units together rather than the space driving them apart. So the degree of swelling is less for vermiculite compared to smectite. For this reason, vermiculites are considered as limited expansion clay minerals, but expanding more than kaolinite, but less than smectite. So remember that vermiculite expands more than kaolinite, but less than smectite. You should remember the sentence because you will get confused in your objective type of questions. Vermiculite expands more than kaolinite, but less than smectite. The cation exchange capacity of vermiculites, CEC, usually is higher than other silicate clays, including montmorillite and other smectites. See, cation exchange capacity is more in vermiculite compared to montmorillite and other smectites because of very high negative charge in the tetrahedral sheet. Vermiculite crystals are larger than smectites but smaller than kaolinite. So you should remember these sentences. So that is expanding type of clay minerals. I will send you the drawing. I will share that diagram. I am not able to share what is happening. Only the host. I am the host, right? Not able to share. I will send the diagrams. I'm not able to share here. I don't know why. Only the host can share in this meeting. It is coming. I will send you the diagrams later. Okay. So that is 2:1 expanding type of clay mineral. Coming to the non-expanding type of clay mineral, example, mica. These micas are type of minerals belonging to 2:1 type. And some other examples are muscovite and biotite. And here, the weathered minerals have similar in structure, and they are found in clay fractions in the soils. They are fine-grained micas. Here, the clay formed after weathering of biotite and muscovite, the clay mineral formed is illite, ILLITE. That is 2:1 type of clay mineral. Example, 2:1 type, non-expanding is illite. Similar to smectite, fine-grained micas have 2:1 type of crystals. Here, the particles are much larger than smectite. And the major source of charge for these clay minerals are the tetrahedral sheet, where aluminum atoms occupy about 20% of the silicon sites. The diagrams I will post it to you later because I'm not in shape. I don't know what's happening. So these, because of the presence of more aluminum ions, there is high net negative charge in the tetrahedral sheet, even higher than that found in vermiculites. So to satisfy this charge, potassium ions are strongly attracted to the interlayer space and are just right size to fit into the spaces in the adjoining tetrahedral sheets. The potassium, therefore, acts as a binding agent, preventing the expansion of the crystal. Therefore, fine-grained micas are non-expanding. See, if I write on the board and explain to you only, you may understand, but again, you go on reading the notes what I sent and practice drawing those clay structures, then you will understand. Yet, if you find a difficulty, I think when you come back, I can explain to you. So you should know the difference. 2:1 expanding is montmorillite, 2:1 non-expanding is illite. Because of the entry of potassium ion into the illite interlayer spaces, they do not expand. Therefore, that is called as non-expanding clay minerals. Here, the properties such as hydration. Hydration means entry of water, absorption of water, cation absorption, swelling, shrinkage, and plasticity are much less intense compared to smectite. So the fine-grained micas, they are exceed more than kaolinite with respect to the characteristics. But this may be due to the presence of interstratified layers of smectite or vermiculite. Comparing the size, the fine grain sized mica crystals are intermediate between the smectites and kaolinite. So the specific surface area varies from 70 to 100 square meters per gram. That is about 1/8 of that for smectites. So that is 2:1 type of clay minerals which are non-expanding. That is because of presence of potassium ion in between the interlayer spaces. Next, coming to 2:2 type of clay minerals. Here, example is chlorite, CHLORITE. You should know the examples of different minerals. 1:1 kaolinite, 2:1 type. Expanding type is montmorillonite, non-expanding type is vermiculite, 2:2 is chlorite. So what is chlorite? Define chlorite. Chlorides are basically iron, magnesium silicates with some amount of aluminum. So it has a typical structure having 2:1 layers, similar to the layers you have seen in vermiculite, with alternate magnesium dominated trioctahedral sheet, which gives us 2:1:1 ratio. So 2 silica layers, 1 aluminum layer, 1 magnesium layer. So you have 2:1:1. Magnesium dominates in the trioctahedral sheet in the 2:1 layer of chlorides. Therefore, this crystal unit consists of 2 silica tetrahedral sheet, 2 magnesium dominated trioctahedral sheet, giving rise to the term 2:1:1, or sometimes it is called as 2:2 type of structure. So when it is 2:2 or type of structure, means it will have more negative charges, and therefore it is able to absorb moisture, or cation exchange capacity will be less compared to montmorillonite, because particle size and surface area of chlorides are lesser compared to montmorillonite. Therefore, no water adsorption between the chloride crystal unit take place because of its non-expanding nature. So these are the examples of 2:1, 2:2 type of minerals. Next is the mixed and interstratified layers. So you should know this is a classification of minerals based on arrangement of silica and aluminum sheets in the clay minerals. So we finished with 1:1, 2:1, 2. Now mixing both mixed and interstratified layers. Here, specific groups of clay minerals do not occur independently with one another. For example, in a soil, we find several clay minerals in mixture. Mineral colloids will have properties and composition between either 1:1, 2:1, or 2:2 type of clay minerals. So such minerals are termed mixed layer or stratified minerals. Examples are, in some examples again in that are interstratified layers are mixture of vermiculite, mica, smectite mixed between. So it may be have a vermiculite layer, it may have a smectite layer, or it may have a mica. So that is called as interstratified layers. And in some soils, there may be single structured minerals like montmorillonite. So these are the examples of different clay minerals. So examples in some soils, I'll give you examples of type of clay minerals present in alluvial soils. In alluvium soils, clay minerals found are chlorite, montmorillonite is present in flood plains and basins. Even kyanite is present in alluvial soils. In forest type of soils, illite, chlorite, montmorillite, kyanite we can see. Black cotton soils, we can see smectite, illite, chlorite. Desert soils, we can see illite, attapulgite, vermiculite. In red and lateritic soils like Jikevike, we can see kyanite, gypsite, chlorite, illite. So these are the examples of these layer silicates. These are all crystal clays. These clays are crystallized. Coming to the amorphous type of clays or powder form of clays, which do not have fixed structures like shapes, hexagonal or tetrahedral or octahedral. So they are amorphous clays. Amorphous clays are a mixture of silica and aluminium that are not formed well-oriented crystals. They are not minerals because they lack crystal formation. They are amorphous in nature. These clay occur where large amounts of weathered products exist, but they do not have the conditions or time for formation of crystals. So amorphous clays are common in soils formed from volcanic ash. Usually in Japan, we find this type of clays where volcanic ash is present. So such clay minerals are called as amorphous clay, and example is allophane, ALLOPHANE, allophane. So the properties of such amorphous clays are they have high positive charges. If they have high positive charge means they will attract opposite charges means negative charges. So they will have high anion exchange capacities and or even high cation exchange capacity because almost all the charge is from hydroxyl ions, which can gain a positive ion or lose a H plus ion attached to these clays because they have variable charges that depends on how much H plus is present in the soil solution. So amorphous clays are not crystallized, they are ash type, they have high negative charge, therefore they have high positive charge, therefore they can attract many anions. Because of H plus ions, they can attract cation, negative charges also, negative cations, and anions are high in such type of amorphous clays, depends on the soil acidity. So that is amorphous clays. Next type of clays are sesquic oxide clays. So these are all classification of clays. Layer silicates, one is over in the among layer silicates, 1:1, 2:1, 2:2 type of clay, amorphous clays. Now, sesquic oxide clay. Sesquic oxide means iron aluminum oxides. F2O3, Fe2O3, Al2O3. They are oxides. They are metal oxides and hydroxides. So, under these conditions, where there is high rainfall and high leaching, high intensive weathering, in humid warm climates, most of the silica gets leached from the soil compared to nitrogen, and this nitrogen has a negative charge, NO3, nitrate nitrogen, is not held by the soils but remains free ion in, that is ion, sorry, sesquic oxides are iron aluminum oxides. So here in humid warm climates, much of the silica and alumina are dissolved and get slowly leached away. So the remaining materials which have low solubility are iron oxide, aluminum oxide. They are referred to as clays of iron and aluminum because they are written as Al2O3, H2O, Fe2O3, H2O, and the hydration differs. These clays are maybe amorphous or crystalline, and they do not have swelling property. They are not sticky. They do not behave like silicate clays. So examples are gibbsite, 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 and geotite. You might have seen these two minerals in the lab. So these are the inorganic colloids. So you're clear about inorganic colloids. So inorganic colloids are layer silicates, SAC oxides, then amorphous clays. There. The organic colloid. Coming to the organic colloid is humus. Humus. Humus is the organic colloid. Humus is amorphous, dark brown to black in color, insoluble in water, but mostly soluble in dilute alkali, that is sodium hydroxide or potassium hydroxide solution. And it is the end product of organic matter decomposition. So the humus is referred to as an organic colloid because it consists of various chains, linked carbon atoms. They are not crystalline, they are powder form, they are not crystalline. They mainly have carbon, hydrogen, oxygen, then silicon, aluminum, they do not have all these metal ions. So these organic colloidal particles vary in size. They may be very small as silicate clay particles. The negative charges of humus are associated with dissociated phenolic groups, OH groups, carboxylic groups, and therefore the size varies, and the properties of this organic colloid also has high surface area, high charge density, high cation exchange capacity, high water holding capacity, high nutrient retention capacity. So this is organic colloid. So this much is enough for today's class. So we are clear about soil colloids, classification, silicates, tetrahedral structure, octahedral structure, dioctahedral, trioctahedral, then different type of layer silicates. I will send that remaining notes to you so that when you read, you can understand, and I will be giving you few assignments after few more classes. Okay, fine. You have taken the attendance, you have taken the screenshot?
Yes, ma'am.
Okay, you send it. Fine then. This much is enough for today's class. Otherwise, you'll get confused.
Okay, ma'am.
Okay. Okay, fine. You can leave the meeting.
Thank you.
Okay, fine, fine.